So hello everyone, welcome again to another RADNEXT facility webinar. So my name is Igor Aguiar from the RADNEXT Project Management Office. And before introducing the speaker, I would like to just introduce a little bit on the project. I'll share my slides. Um, so I hope you can see it perfectly. So RADNEXT is a European-founded project with the main goal to provide an infrastructure of facilities that can accommodate radiation testing in Europe and to facilitate the access to facilities for this type of irradiations to qualify electronics under radiation. So the project has already provided about 6,000 hours of beam for different type of beams, neutrons, protons, and heavy ions, and other different non-conventional beams. We usually have 3 calls for proposal per year, and now we have an ongoing call in this month. So if you have any project that you would like to irradiate and qualify for radiation hardness, please be aware that the deadline is next week. Due to the success of the current RADNEXT project, we have a follow-up project proposal ongoing, and we want to submit by the end of this year and hopefully get the funding from the European Commission. So the current call for proposal is the deadline is next week, so 31st of May. And for the available beams, we have from neutrons to different proton energy, heavy ions, and electron and photon beams. We also have a user support expert team that provide technical support for users when writing the proposals. So if you have any doubt or if you need some support on writing the specification for your radiation plan, you can contact the RADNEXT user support expert team. Or if you have general questions, you can also contact us through the RADNEXT TA Transnational Access email. If you want more information, you can also go on our website where you can also learn about the research activities that we carry on during the project. We are also very active in the social media, so on LinkedIn. If you want to know about this call for proposals, other opportunities in the network, the events that we are organizing, so please follow us and be updated with our opportunities in the network. Also, all users from the RADNEXT user being they need to provide a report, so a summary report of the irradiation. So if you want to get to know what is being done in the past during the project, you can access through the Zinode, which is an open repository. And there you will see all different type of research and irradiation campaigns that have been done through the transnational access at RADNEXT. And today we are here for the facility webinars. So last month we had one on HARTS, where I had my colleagues presenting the HARTS project with higher energy heavy ions irradiation. Today I'm happy to have here Dr. Henry Clark that will present us the SE testing at the Cyclotron Institute. And the next month, we're going to have another facility presentation also on heavy ions. So today we have Harry Clark, which is the scientific in charge for the facility of SE testing in the Cyclotron Institute. So Dr. Henry Clark received his PhD in experimental nuclear and high energy physics from Ohio University and has been working in the Cyclotron Institute ever since in the development of the K500 cyclotron and in the project management of the radiation effects program. So it's with my pleasure that I will pass the mic to Henry and learn a little bit more about this very nice SE testing facility. So I will stop the sharing And the floor is yours, Henry.
Okay, so let me start my PowerPoint here. Um, then let me share. Is that looking correct?
Yes, charging. Yeah, perfect.
Okay.
Thank you.
Okay. Let me adjust my screen here. Okay. So good afternoon or good morning from wherever you're sitting today. And thank you for having me on the RADNEXT webinar series. Today I'll give an overview of SCE testing at the Cyclotron Institute at Texas A&M University. As presented, I'm Henry Clark. I'm an accelerator physicist and a manager of the Radiation Effects Facility Program at the Cyclotron Institute. And I've been at Texas A&M for nearly 32 years. Am I showing the? Okay, hold on. I'm having a technical issue here. Okay, here we go. Okay, slide 2. Everyone see slide 2?
Yes.
Okay, thank you. So my presentation today is broken into 3 areas. First, I'll show the Cyclotron Institute, the facility equipment that we have, and the beams that we provide, and then we'll go into the radiation effects facility where we have 3 SEE beam series. I'll talk about our dosimetry system and other equipment that we have for our users. I'll show some statistics and the user groups that traditionally come, and the K150 Cyclotron upgrade project, which is a very important project for the future of the laboratory and for the SCE community. I'll also discuss our workforce development programs and radiation effects. We have an annual cyclotron NASA boot camp, and also our master's degree program in applied physics. So where are we? The Cyclotron Institute is located on the main campus of Texas A&M University in College Station, Texas. The driving distances from major airports, Houston is about 137 kilometers or 1.5 hours away. Austin is about 177 kilometers, 2 hours away. Dallas is 241 kilometers away or 3.5 hours. We also have a local airport here in College Station called Easterwood that serves American Airlines commuter flights from Dallas. They're like 4 to 6 flights per day, depending on the day of the week, and the flight times are under an hour. So let's just take a moment here and discuss how cyclotrons work. They work on the principle of the Lorentz force equation. Force, which is a vector, times charge times electric field, which is a vector, plus charge times velocity, which is a vector, crossed with the magnetic field. Once the charged particle enters the center of the cyclotron, the oscillating electric field provides a linear force over these gaps to increase the velocity. A fixed magnetic field provides an inward pointing force for the circular orbit where the radius increases with velocity. A particle can take several hundred turns before exiting the cyclotron. Our K500, the number of turns is about 500. Our K150, it's about 200 to 300 turns. Energy is expressed in energy per nucleon because of the cyclical nature of the cyclotron. And energy per nucleon here, as I show in this formula down here, is equal to the magnetic field times the charge to mass squared. And it's also proportional to the cyclotron frequency. The cyclotrons at Texas A&M are variable energy cyclotrons. That is, the ratio frequency and magnetic field systems are tunable over an operating range, and it can accelerate to a wide range of ion types over a wide range of energies. So variable energy machines are designed to do everything that's possible within their operating range, which makes the cyclotrons at Texas A&M perfect for SCE testing. So here's a layout or cartoon showing the Cyclotron Institute facility. The major equipment involves 2 cyclotrons, which I'll discuss in more detail in the next slide. We have 5 ion sources, 3 ECRs, which are positive ions. So we have 2 here on the K500. These are first generation ECRs. We have a second generation ECR as the 3rd ECR on the K150. Also attached to the K500 cyclotron is what's called a charge breeding ECR. It charges up positive ions as well. This is a 2nd generation ECR, just like the ECR that's on the K150. But also on the K150, we have a negative ion source. So we can actually flip the field of the cyclotron up and down, depending on whether it's positive ions or negative ions coming from either one of these ion sources. This negative ion source makes both H- and D- beams. And coming out of both cyclotrons, we have 9 experimental beam lines for the various science and applied physics programs, 2 of which are the SEE beam lines. So here you can see the ions come from the ion source through the cyclotron down this beam path and then to this testing area here, which is known as the radiation effects beamline for the K500. Ions can come from this ion source or from the negative ion source into the cyclotron, take turns, come out, and then down this beamline here, which is the radiation effects facility beamline for the K150 cyclotron. Our K150 cyclotron, or which is known as the 88-inch, it's a copy of the Berkeley 88. This machine was brought on a little bit later, a few years later than the one at Berkeley. It celebrated its 50th anniversary in 2017. It's a conventional water-cooled magnet field. It's a conventional water-cooled magnet with fields up to 1.5 Tesla, hence the 150 of K150. The magnetic radius is 44 inches. Radio frequency spans between 5 to 16 megahertz. It can accelerate protons up to 50 MeV through the H- technique and extracted with a carbon foil. The nice thing about the carbon foil extraction technique is that 100% of the beam is extracted from the machine. It can accelerate deuterium and helium-2+ up to 20 MeV per nucleon. And we've made heavy ions up to 10 MeV per nucleon, up to xenon, extracted with an electrostatic deflector system. The K500 superconducting cyclotron, the first beam came on in 1988. This was a project that spanned a good part of the 1980s in terms of development and design, and finally the ability to make heavy ions. It's a superconducting cyclotron magnet using niobium titanium wire. It's cooled with liquid helium to about 7 kelvins with fields up to 5 Tesla, the 5, hence the K500. The magnetic radius is 31 inches. Radio frequency is between 10 to 30 megahertz. Can accelerate up to 72 MeV per nucleon. And we've done this for molecules such as H2 and deuterium ions, or it can accelerate alpha particles up to 72 MeV per nucleon, which reaches about 37% of the speed of light. The heaviest ion beam we've accelerated with the K500, it was uranium-238 at 12 MeV per nucleon. And all the beams are extracted with a double electrostatic deflector system. So this is a scatter plot of the energy per nucleon versus atomic mass number of what we can make with the K500 and K150 cyclotrons. Here we're showing, here at the top, the highest energy per nucleon beam, which was a 72 MeV per nucleon. And this over here showing us the heaviest particle that we've accelerated to the highest energy, which was 12 MeV per nucleon. However, providing all the beams that the cyclotrons can make it's not practical for SEE testing. Some of the beams are either very difficult to make from the ECR ion sources or are hard on the operation of the cyclotron. And so for SEE testing, we chose beam series that give essentially a 99% chance of working for the customer when they come to use the beams. Which brings us to the radiation effects facility. We'll talk about the 3 beam series, our dosimetry statistics, and then the upgrade project. So our 15 MeV per nucleon series provides ions from helium all the way up to gold, which provides an LET range from less than 0.1, or excuse me, less than 1 up to essentially 94. It also provides enough range up to greater than 100 microns in silicon. Okay, the K500 can provide all of these beams from helium to gold. The K150 can only provide helium up to krypton currently. We're going to talk about advancing this beam list with the upgrade project later in the talk. We also provide from the K500 cyclotron the 25 MeV per nucleon and 40 MeV per nucleon beam series. 25 MeV per nucleon provides helium up to xenon, and our 40 MeV per nucleon series provides nitrogen up to krypton. And you can see here that the ranges are much greater, hundreds of microns in silicon, but still being able to provide LETs from less than 0.1 all the way up into 60, the high 60s with the xenon. The krypton from, of course, less than 1 up to an LET of 41. The beams that we provide annually for the radiation effects SEE testing program, about 80% of them come from the 15 MeV per nucleon beam series. About 19% come from the 25 MeV per nucleon series, and less than 1% are actually the 40 MeV per nucleon series. Before NSRL came on, 40 MeV per nucleon was really starting to pick up. We were doing that more often, but once NSRL got into the mode of providing a fair amount of beam time for SEE commuting, our community, our 40 MeV per nucleon series beams weren't requested as much. These are the most difficult beams that we make and take quite a bit of time to tune up. So using nature as our friend, the ions in each series for the K500 were specifically chosen since their charge to mass values are very close to each other. However, not so close to produce the wrong beam from the cyclotron. Most of the cyclotron parameters are averaged, which in turn saves tuning time from one ion to the next. The critical values for the K500 are the superconducting coil magnet values here, which I'm showing as A and B. And so for the 15 MeV per nucleon series, we have a range around 0.2. If you look over here at an example of argon 40, 8 plus 8 divided by 39.964 is 0.2002, which is showing this charge to mass here. The resolving power of the K500 cyclotron is much greater than this last decimal place here. So we're, even with ions that have charge to mass ratio this close, we're able to resolve them cleanly with the K500 cyclotron. Then to move to the copper, krypton, and so on, up to praseodymium in this energy, or charge to mass range, it's changing the magnetic field, which takes the time. The holmium through gold series, we use a 0.182 charge to mass ratio. These are also very close. For the 25 MeV per nucleon, we use a 0.275 charge to mass ratio for ions from neon up to xenon. And then for the 40 MeV per nucleon, we use a 0.35 charge to mass ratio series. Note that for the K150, to get to 15 MeV per nucleon, we use the same 0.35 charge to mass ratio to make the beams for that cyclotron. Here you can see, once again, energy per nucleon is the magnetic field times charge to mass squared. So if your magnetic field can't get you can't increase your magnetic field. The only way you're going to raise your energy per nucleon is by increasing the charge to mass ratio. And so we have an estimated beam change chart, which our customers use for planning. You can see that it's anywhere between 25 minutes if you stay within a beam series up to 2 hours. So if you're going to switch from a 15 MeV per nucleon to a 25, it's going to take time because when you're in a particular series, we're just changing the beam in the ion source and we're changing the main field of the cyclotron. Whenever you switch from one beam series to the next, now we're having to change the RF plus the parameters of the cyclotron, the injection line, and the beam line. So there's more time added. Very, very infrequently do we have customers that switch energy series. They generally stay on the same energy series and change ions within. If they need to change to different energy series, they'll come back on a second day or third day. One interesting thing about the K150 cyclotron, since it's a very simple machine with regard to the K500, is we can do what's called a cyclotron frequency shift technique, where the cyclotron magnetic field is kept fixed, but we change the magnetic field is kept fixed, but we change the frequency. So the energies change slightly, but not too much. But the frequency RF change is only on the order of seconds or 2 minutes. So we can change from nitrogen to copper easily within 5 minutes or so. As we have evolved the K150 cyclotron, this ability to do frequency shifting technique, we hope is going to become very valuable. So customers can switch from light ions to heavier ions quickly without a lot of the wait time. So K500 has its advantages because it has a much larger range of ions that it can make, plus it can do much higher energy. The K150 has the ability to, in a very specific ion range, be able to switch its beams rather quickly. So here's an example of how cyclotrons, once again, provide a really nice beam for the SEE customers because customers need a broad uniform beam. Cyclotrons inherently have a very large emittance, so the beam coming out of the cyclotron here is broad. And what we do is we use an over-focus technique for our quadrupole pairs to grow the beam as it comes out of the cyclotron enough to transport it down the beam line so we don't lose a lot of the beam. But then as it moves further and further down, each one of these quadrupole magnetic pairs grows the beam even more and more. What's important, though, is at the very end that the beam is uniform over a 4-inch beam spot. Now, what we use for our dosimetry system is a 5-YAP scintillator system. Here you can see over to the right the 4 outer counters and the one in the middle. Each one of these scintillators is covered with a precision-made 0.1 centimeter thick collimator. That allows for a situation where no calibration with other beam detectors are required. So since we know how many counts are coming out of each one of these scintillators, we multiply those counts by 10, which gives us the actual flux seen in each one of these counters. The 4 outer counters are placed outside as close to the beam pipe, 4-inch beam pipe as possible. And they monitor the beam even when the shutter is open. So when the shutter opens, this guy drops out, the middle one drops out, the beam continues through this hole, and these 4 outer counters keep measuring the beam flux and continue to monitor and measure the fluence. Before we ever give the customers the beam, the goal is to make sure that these 4 outer counters plus the middle counter are counting pretty much within a few percent, within 10%. The shift left and right or up and down is known as the central shift. Axial gain is known as the ratio of the 4 outer counters, the average of the 4 outer counters divided under the count rate of the scintillator in the center. And what we shoot for is a goal between 1 to 1.1 of that ratio of the 4 outer counters divided under the count rate of the central scintillator. As I mentioned, this center one drops out, and that ratio is retained through the course of the run until the fluence is reached. One of the real benefits of a system like this is that it creates a redundancy in the sense that if we only had one particle detector detecting the flux and fluence, if that detector was working improperly, we wouldn't know unless we had some way of comparing it. So by being able to compare all the scintillators to each other and seeing that we get the right count rate, we know that the system is working correctly. We also provide a degrader system on both beam lines. The one on the 500 has 9 foils because we can go to much higher energy. It's in steps of 2, so 1 mil, 2 mil, so on and so forth. It rotates up to 60 degrees. So once you get 1 mil up to 60-degree rotation, you know, the cosine, 1 over the cosine of the angle gives 2, and so on. So and also the foils fully cover the 4-inch beam spot. So the scintillators downstream that are doing the dosimetry see all particles that are degraded by the beam. One of the really nice features of having a degrader system like this also, not only to change the energy, but it's also to show the customers that we're giving them the correct beam. So knowing the range in aluminum, you can put in that amount of thickness in order to stop the beam for this particular ion. Okay, so all of the features of our facility are shown here on this very, very busy plot. We have a patch panel system that allows various connections, serial BNC Cat6, USB network. We also have beam trigger here. There's a air path ruler because most of the testing here, almost 99.999% testing that's done here is done in air. In order to understand the energy of the particle at the surface of the part, you need to know how much energy is lost from the beam path. So we have this laser ruler that measures that. We provide all kinds of voltages. We can make different beam spots between 25 to 44 millimeters. We also have a safety cap to work safely around the end of the beam line so you don't puncture the window. The frame here or this platter can move X, Y, Z, theta, and phi. It's remote controlled through our dosimetry control system, which I'll get to in a minute. Back here is where that degrader chamber is that we were looking at in the previous slide. We have a vacuum chamber, which almost nobody ever uses anymore because the beams have enough range to make it through several centimeters of air and also still have at least 100 microns of range in the device. We center our parts using a beamline viewing camera here. The SEUSS dosimetry software is controllable down in the cave on the beamline, also in the data rooms, and then also in the control room where our operators sit. They also can help the customers get through any of the questions with the dosimetry system. The YAP detector system is in this box here. We provide dry nitrogen and compressed air, and also a heat gun system, which has become very popular. So a lot of times customers need to heat up their parts to a particular temperature in order to test for latch up or burnouts or whatever. Power devices have problems with temperature. This is a controlled heat gun system that it can be regulated either by a thermocouple or by in an infrared camera through a feedback loop. So here's an example here on the beam line. The beam is coming out this nozzle. The part is buried in this board here. You can't see the part. And the heat gun is right here, and it's heating up that part. And so the infrared camera is looking in from this angle right here, and this is what it's showing here. So you can see the Texas A&M logo here. That's the Texas A&M logo here. And you can set a region of interest with this FLIR camera through the software to maintain that temperature on that part. So it also has a strip chart. So customers know that during the time that the part is being irradiated, that the temperature of the part is being held constant. And also that the software is controllable from the data room, so they can turn the power on and off or the heat on and off to the heat gun remotely. They don't need to be down in the cave. So our SEUSS Dosimetry and control software is home built, and here you can see the front panel has all the different current settings, log file, the beam that we're running, any layers, the energy of the beam after the layers that stop the beam, the range in silicon, LET, on and on and on. Okay. And then over in here, there's all kinds of other features to go to customize whatever setup the customer wants. And here you can see the 5 scintillators being counted here on this part of the screen here, the beam characteristics screen showing the uniformity, central shift, axial gain, and the current flux of ions. Some of the key features of our SEUSS dosimetry software is it's written and maintained in-house. It provides all the dosimetry information, fluence, flux, LET, dose, range, and time. It allows for preset fluence, timer upsets. One of the nice things about the K500 cyclotron is we can actually stop the beam within microseconds. If you deliver a pulse, a TTL pulse or a logic pulse, and then when the logic pulse drops to 0, then the beam returns. So you don't necessarily have to use the shutter to stop and start the beam. It has a layer file routine for determining the effective LET and range, has shrim built into it for determining LET and range of each ion, the sets of aluminum degraders, the desired LET, it saves all the parameters and saves everything to an electronic log file so that you have it when you leave the facility. The demo version is downloadable off of our website and can operate on Windows 10 or 11. Here's a diagram of the facility itself. You sit up above, the beam line is down here. If you're on the K500, cable lengths are 20 feet. K150 cable lengths, if it's custom cables, is 80 feet. However, if you want to use our patch panel, that's already there. You just connect from the desk to the patch panel, and then from the patch panel to the DUT in the cave. We have a nice setup area on both the K150 and K500. This is showing the K150 setup area. That's the data room back there. The data rooms are climate controlled, and they even have Venetian blinds so that other people who are setting up for the next shifts of beam aren't watching what you're doing in there. And so this is showing the statistical use of our facility from the beginning. Our first beam was actually a hydrogen molecule for NASA Johnson back in 1995. We weren't even providing heavy ions at the time. And as the need for heavy ions came in the 1990s, we then developed the heavy ion beams from the K500 cyclotron for SEE testing. This increase as we're going up here is a combination of our ability to develop more and more beams, develop a better product for the customer, but also the need for the community. We didn't have the need for 4,500 hours back in the beginning. And so as time evolved and we added in new things like in-air testing, higher energy beams, then the K150 cyclotron came on. We could offer protons and some light ions. That allowed us more availability. And then as we developed the K150 cyclotron to make heavy ions, then the ability to provide more and more ions increased. Up to date, we've provided about 80,000 hours to the community. And the kinds of groups that come are aerospace, space exploration, military, even the autonomous vehicle industry is coming. And from the US, you could see all the major players come to the lab. We also have quite a few international radiation effects facility users from Europe and from Asia. Right now, we have about 20 or so that come. And here are the various names of the different agencies and companies. And looking at the overall operation annual operation of both of our cyclotrons, Here you can see out of the two cyclotrons, you get over 17,000 hours. Maintenance is something that never changes. 6,000 hours goes to science, about 4,500 hours goes to radiation effects, 4,000 from the K500 and about 500 from the K150. But what I want to point out here is that we have quite a bit of time that we can still develop with our K150 cyclotron. So the 500 is pretty much fully scheduled. The K150 has lots of availability on it, but the beams that we have currently are able to make are not really, the list needs to be expanded. Which brings us to the K150 cyclotron upgrade project. So the K500, the most requested beams are the 15 MeV per nucleon series of helium up to xenon. Okay. Currently, the K150 cyclotron only makes helium up to krypton. We need an upgrade of this cyclotron in order to be able to produce silver and xenon. Currently, the K150 cyclotron has a second generation ECR ion source on it, and it produces, like I said, krypton 27 plus, but it's very difficult and the intensity is generally low. If we're going to make silver and xenon, silver at 38 plus and xenon at 43 plus, which are needed for 15 MeV per nucleon, we need a much more powerful ion source. And so the current source that we have here is what's known as a second generation source. Third generation source is the Venus source. However, we feel that an ion source in between, which is a hybrid between normal magnet and superconducting, would be sufficient. An 18 gigahertz source with a 2.4 Tesla maximum magnetic field would be the proper source to add to the cyclotron. And so the Pantechnique company is building us an 18 gigahertz ion source with a complete diagnostic system. It's known as PK2TXIIIS. It's Pantechnique with Texas, everything, and 2 Tesla all kind of marriage together there. It's an ion source here with analyzing magnet and 2 focusing elements, one at the entrance and at the exit, and a complete diagnostic station. What's great about this project is they can build this in the factory and test the beams from the ion source before we ever bring it to the cyclotron and put it on the K150. Now, we're not going to get rid of our existing 14 gigahertz ion source. We're going to move it. And so the dashed lines here represent what is currently there here at the lab. So this is connected currently right here. So we need to move this ion source over, and then we need to add in these beam lines in order to connect both the 14 gigahertz and the new Pantechnique source to the K150 cyclotron. This is the top of the cyclotron. The beams go down in here. So there's quite a bit of work that has to be done. But we're really moving along on this project. Beamline components are received. We've received most of the power supplies and vacuum equipment. Support structures have been received. The 18 gigahertz source at Pantechnique is coming together nicely. First beams are supposed to come out in August and in the fall. Maybe transport it to Texas A&M in the spring of 2026, and then we can start developing beams by the fall of 2026. How am I doing on time? Do I have a few more minutes?
Yes, you still
All
have.
good, yeah. Yeah.
Okay. I hope I didn't rush too much, but I see the clock is ticking. So then my last few slides are the discussion of our workforce development program in radiation effects. Annually, we do what's called a TAMU NASA boot camp. We've done it for 5 years. The first year was done over the web because of COVID, but the last 4 years we've done in person. And what it is it's for students and early career researchers who want to get a really broad retrospect of what it takes to be radiation effects testers. And so we do. We were very careful about who we select to come to the class. But what it does is it creates an opportunities to network with commercial and government agencies to develop this really critically needed workforce. It's what we've landed on is a 4-day series where in the morning we do classroom work, and then in the afternoons we do in-beam testing with analysis. And we rotate between the different groups. We generally have somewhere between, I don't know, 18 to 24 students. We break them up into 3 groups, while one's in the beam, one's analyzing, and then we also talk about other things with radiation effects testing. We also have a lunch and learn every day, which allows for even more knowledge to be soaked in by our students. We've had a very positive response from this NASA boot camp. We typically have it in late February, early March. That's when we're coming out of our annual maintenance period, and is a great way to test the cyclotrons. The parts that we test in beam are well characterized and well known, so we kind of know which beams that are going to show the most response, so that the students get the best experience here. And it really doesn't require more than a couple of beams, or maybe one beam, and using the degraders to change the LETs to show the responses to different LETs. We also have a master's program in radiation effects. This is with the physics department here at Texas A&M. The cyclotron provides the resources for the students. In other words, we provide the beams, we provide the materials that they need in terms of power supplies, oscilloscopes, whatever it is that they need in order to do their project. But they earn their degree through the Texas A&M University Physics and Astronomy Department. It's designed to be a very hands-on experience with PC board fabrication, computer programming, data collection, and analyzing the data, which is really the 4 very critical points of radiation effects testing. Understand your part, knowing how to build a board, how to program, and how to take the beam and how to take data in the beam, and then analyzing the data afterwards. So it's the 4 critical areas that really sets up students to have successful careers in radiation effects testing. So building a PC board is actually a very important part of the education. We have our own what's called CFAB for building boards. They can design, you can use the design software to design the board. It has a PCB mill, reflow oven, pick and place, stencil press, UV curing chamber, soldering station, everything you need in order to build your PC board. What our students have learned from this process is in general, they build bad boards. They're very noisy and the data comes in, awful. And then they learn how to create better and better boards. So they learn an awful lot, and they take quality data rather than noise off of their PC boards. And that's my last slide. So anyone who's interested in using the facility, you contact me directly. View our website also for more information about the facility. So there's quite a bit with regard to this facility that I cannot cover in a 40-minute time period. So thank you for your time and your attention.
Thank you, Harry. I will just stop the recording now.